All right, now we're going to add an element to this. Now, if expected value is the basic math of things like roulette or poker, present value and future value is the basic math of thinking through time. This allows us to make comparisons between a dollar today versus $100 in the future. Which is worth more? Well, we need to add a little bit of assumptions, a little bit of structure to say that, but these concepts are going to let us do that. So, present value, we're thinking about what is something worth now. The future value is what is that thing going to be worth in the future when we take account of compounding interest. And this allows us to move from the present value to the future. And when we rearrange a little bit of algebra, we can move back again. So we can say, given some future value, what should it be worth now? So, classic example of expected value would be the game of roulette, right? You play the game, the outcome happens within a few minutes. A classic example of present and future value would be a lottery where they're offering you a prize of something like $1 million a year for the next 30 years. So let's think about this. We've got a lotto. This is a good thought experiment once I write this down to pause and think through. So you get $1 million per year for 30 years. So, two ways we could ask this. One is, how much should this be worth? And another is, would you rather get, say, $20 million now? So this, it adds up to $30 million, but not all of those millions are happening at the same time, so some of them are going to be discounted. So we think about this, we get 1, 1, 1, 1, 1. Let's just think 5 years into the future. $1 million now is worth $1 million. $1 million in 1 year, we can ask the question of how much would I need to put away so that with compound interest it grows to be $1 million? And the answer there is going to be something like $950,000. Right? You put away $950 in a year, you're going to get about $1 million with a little more than 5% interest. 2 years out, you're going to need to put away less money. It might be something like $890,000. 4 years out, you're going to need even less money. Maybe that's going to be $820,000. And let's just kind of make up a number here. Let's call this $750. So we add these up, and it looks like $5 million, but this is the undiscounted. What we care about is the discounted. This is kind of the flip side of compounding, discounting. The discounted value of $1 million now is $1 million, plus $1 million in the future is less than $1 million, and less than that, and less than that, and less than that. And this ends up being, I'm going to do lazy math here and call this about 4 million. It's not, but we're going to get the computer to do the hard math in just a second. So, not legitimate math, but giving us the basic intuition. Getting this prize over time, with most of it coming to you in the future, means it's actually worth less than $30 million. Now, is that discounted value less than $20 million? Well, to understand that, it's going to be a lot easier if we use a spreadsheet to do the hard work for us. So I'm using LibreOffice. It does the exact same thing as Excel or Google Sheets or Numbers on Mac or whatever else. So we're going to set this up so that we've got 30 years, starting at year 0, going up to year 29. We have got 30 things to add together, right? 30 rows, 1 column, 30 payments we're going to consider. And each of these payments is $1 million of undiscounted value. So what do we need? We need what we're going to call a discount rate. And just to be lazy, I'm going to call it 5%. So right now, as I'm recording this in 2023, you can get a treasury bond for about 5%. You put away $100, in about a year, you're going to have about $105. Or you put away 95 cents now, you let it grow, and after a year, you're going to have about $1. So our discounted present value. Well, you know what? This is going to be a little bit easier for me with the math. So let me quickly write out the formula. If you freeze up when you see equations, don't panic. So we're going to start with compound interest, where we're asking what is the future value. It's going to be the present value, and we're going to get some interest, 1 plus r, right? So if r is 5%, that's our interest rate. 1 plus 0.5, that's going to be 1.05. And then we're going to have an exponent here. This is where it gets a little scary, but I promise exponents are not that difficult once you practice with them enough. T for time. And what this means is, let's say we're thinking about compounding interest over 1 year. Let's just 1.05. 2 years, right? So if t is 2, we're saying 1.05 times 1.05 times whatever our present value is. And a third year, right, we're going to be doing that again. And this is the compounding, right? We're getting our base investment, our present value, plus an extra 5%. And then we're getting that with an extra 5%. And then that with an extra 5%. Right? This is how compounding interest works. And that's why when you start with some present value, it's going to grow like that. And it's going to get steeper and steeper the further it goes. So that's future value. To get present value, we're going to rearrange this. Let me just cover that up. But fundamentally, what we're thinking about here is if we're going to wait until time t. So let's say you're thinking about you're going to retire at age 55. How long is it until then? How much do you need to put away now to meet, some particular target? So with whatever our current present value is, we let it compound until time t, we're going to end up with a future value. But we can do the same thing in reverse, right? We can travel back through time and ask, if we've got some future value and we know how far back in time we want to go, what's it going to end up being, right? So here we're using this math to move forward, but we rearrange it and we can get it backwards, right? And we can change it to find out how much time do we need and things like that. So let's just quickly get that arithmetic out of the way. So future value, I'm going to divide by 1 plus r to the power of t, and that equals our present value, right? So we just moved that over here by dividing, and that's really as simple as it is. Now, I am going to make this a little different. This is going to make it a little easier to put into the computer to get the computer to do the hard work for us. So this is equivalent to saying future value times 1 plus r to the negative t. Right? This is just an exponent rule. You might have seen it back in 8th grade, even if you've forgotten about it. Pro tip, if you're planning on going to grad school and you're going to take the GREs, getting comfortable with exponents makes a big difference on your ability to score well. So now we've got a formula, present value equals some function of our future value, our interest rate, and how long we're waiting, right? Or how far into the future we want to discount to understand how much it's worth today. So, going back to our lottery example, $1 million now is worth $1 million. There's nothing complicated about it, right? $1 million is worth $1 million. But $1 million in a year, we have to ask, what is that future value? And that's going to be 1 plus this. If you aren't used to spreadsheets, these little dollars mean that I'm referring to a cell and I don't want it to change. Let me just give you a really quick Excel lesson right now. So if I say equals C2, I'm referring to the value in this cell. Oops. And then if I copy this and I go down a cell and I paste it, now I'm going to C3. And if I copy to the right or down, as I'm doing this, it moves the reference to the right or it moves the reference down as I'm copying this formula into these different cells. Now, if I instead say with the $sign, whoops, now when I copy this, it's going to refer to the same cell. If I say $C and 2, if I copy this down, it's going to keep the column C, but it's going to adjust the row, right? From row 2 down 1 to row 3, or if I go further down, down to row 6. All right, let's get rid of that. And then just for completion, $2. If I copy that over, right, it adjusts the columns but not the rows. All right, that's spreadsheet stuff. That is helpful. If you're going to work in an office, you're going to be dealing with spreadsheets. Don't panic right now. This is a useful tool, absolutely, but it's not the key thing right now. So, discounted value is our present value, which is going to be the future value times, with a parenthesis, 1 plus this value, to the power of how far are we going. Oops, and let me change the display so we're looking at this. So, and I forgot one little thing, minus that. So, our formula is just what we did on pen and paper. This is our future value in B5 times 1 plus R, where R is going to be 5% the whole time, even when we copy it down. We could get more elaborate, to the power of negative T, so 0 years in the future. That's nice and easy. It's going to just turn into the future value times 1, because the future value is the present in year 0. But for year 1, it's going to be a little bit different, right? It's going to be a little bit more than 95%. And we keep going, and all of these, let's show our formula again. We're just saying this value here times 1 plus our interest rate to the power of negative what year are we dealing with. So when we're thinking 5 years into the future, we need to put $783,000 away for it to grow to $1 million in 5 years. So let's add all of that up. C5 to C35 should capture that. And let's just copy paste this all the way through. So if you're running the lottery commission, you're promising someone, I'm going to give you $30 million over 30 years, but you know that you're not going to have to save up a full $30 million to make good on this prize. You only need $250,000 for the last payment. When we add that all together, what we get is $16.14 million. So what looks like $30 million, because so much of it is coming 20 or 30 years in the future, the discounted value, the discounted equivalent of that $30 million, making that proper comparison, it's only about $16 million. So is it worth accepting $20 million up front instead of waiting to get $30 million over 30 years? If this discount rate is reasonable, then absolutely. Now let's just, as long as we're here, think about this. What the discount rate is doing is it's telling us basically an interest rate or some measure of patience. The more patient we are, the higher this number is going to be. So what should happen to this number? The 16 million should become smaller. I always get this. I'm just dyslexic. Higher interest rate means we are more impatient, right? So let's call this interest rate or impatience. The more impatient we are, the higher an interest rate we need to be willing to save our money, to be willing to wait. At 10%, we are getting a bigger reward for waiting. So if we have a 10% interest rate, you are being rewarded for being patient. Or if you're just a very patient person, you might be willing to have a lower discount rate. So if we think about something like the environment, how much do we care about future generations? Well, if you care a lot, you're going to have a lower discount rate when you're doing cost-benefit analysis on environmental projects. If you don't like the future, if you think that people in the future are going to be worse and not as deserving as people in the present, you're going to have a higher discount rate. And even without getting moral about it, if you are in desperate circumstances, you are going to be less patient because you simply can't afford to be patient. You're going to have a higher discount rate. So what does this mean? If you watch daytime TV, you'll see these ads for things like sell us your cash payment. And it'll be something like you got a lawsuit because of mesothelioma or whatever, and they're paying you $100,000 a year, and some company says, hey, we'll pay you $16 million for your payment. Is it a good idea? Well, if you are relatively impatient, the value to you might be less than the value to the company buying, and so you've got a mutually beneficial trade. All right, let me come back to the pen and paper and recap what we're dealing with. Ignore the math for a little bit. The intuition is what matters. When we go forward in time, we compound our interest. We get something that grows. When we go back in time, we can use the exact same math with a little tiny adjustment. Instead of multiplying by this, we're dividing by this, and we can show that with just a negative exponent. But forget about the exponents. The intuition is compounding. We ask, how much will we get? And then we can say, if we know we're going to get such amount at such a time, how much do we need to put away now to grow to that level? And that's all we're solving for here. Now, there is the other part of this, which is, okay, what if we want to know about t? We're not going to worry about that right now. We can do some algebra and solve for t if we know we've got X amount saved now and you want to grow that to $1 million for retirement. How long do you have to wait? We can do that, but we're not going to do it today. All right, as usual, if you've got questions, let me know in the usual places, and I will talk to you in the future.